This source code will introduce how to analyze signals f of x and images of f of x and y with respect to the intensity oscillation along those variables. I'm going to import a few of the packages we are used to depend on for our code, and then we are going to study periodicity. By that I mean repeated patterns of variation. And we already seen that those mathematical functions sine and cosine are interesting to study periodicity because they are the simplest mathematical functions that allows this kind of study. We also know that sinusoidal functions at low frequencies will show or relate to slow or smooth variation, while high frequencies are related to fast oscillations. So in order to show that, I'm going to create here a space of times of time, and so I'm going to create a variable that changes along time, and this is going to be a vector in between 0 and 1 with step 0, 0, 1 in order to create a number of observations. I'm going to print here the number of observations, so the shape of this vector that we are creating here is going to indicate how many points we are going to sample. So as we see here, we have 1000 points in this vector t, and this means we are going to sample 1000 points, in this case per second. Now we are going to create a sine function that is periodic with period 2 pi along the vector t that I just created. So I will call it my sine. 2 pi here is the period that I want the function to have, so I'm basically converting it so that it has this period that I want, and then I'm going to multiply with t. So I'm basically evaluating the sine at every point of t. And let us create a figure here. And plot it. So I'm going to plot my sine against t, all values of t. And as you see here, this is a complete sine wave. From it starts at 0, 0 and then it ends at 1, 0. This means that it completes all. It has completed all its pattern of wave. If I, for example, change here and say that I want t to vary between 0 and 2, then I'm going to have 2000 observations, and then the pattern will repeat 2 times. But I just want to keep 1 here because I want you to understand the concept of having frequency in terms of seconds. So in this case, this means that we have 1 hertz or a frequency equal to 1, because it's 1 repetition of the pattern along a time t between 0 and 1. We could also increase the frequency, for example, to 4. So in this code here, what I changed here is just this bit. So I'm multiplying everything that's inside the sine function here by 4. So as you can see here, now we have 4 repetitions of the pattern, but along 1 second, still 1 second. So that's what we call 4 hertz, because it's 4 cycles per second. I'm going to change the function, the periodic function, to the cosine, also at 4 hertz. As you can see, we have 4 repetitions of the same pattern. However, it is shifted with respect to the sine function. And as a matter of showing you another example, I'm going to show also with 18 Hertz. As you can see, the amount of oscillation is much higher. Now I'm going to combine all 4 functions to produce one new function. So I'm going to say that my new function is a sum of the sine at 1 Hertz, at 4, and the cosines at 4 and 18. Let us plot this figure. So this is the result. This is the signal that I just produced, and it is a signal that is a combination of sines and cosines at different frequencies. We know, because we created the function, that it has sines in frequencies 1 and 4 and cosines in frequencies 4 and 18. So let us use that same idea we have seen in the previous video and try to match this function with sines and cosines. I'm going to show 2 examples. The first one matching with 4 Hertz, which we know that is part of the signal because we created that in that way, and with 3 Hertz that we know that is not part of the signal. So I'm going to show you, I'm going to define the omega variable as the frequency, and I'm going to match sine of 4 by just multiplying my function with a sine wave evaluated at 2 pi, because it's the period, t, times omega, which is the frequency that I want. And I'm going to do the same with the cosine. And then to see how many points in this function here and this function matches each other, I'm going to print sum of matching sines at 4 Hertz. It's going to be equal to the sum of match sine at 4. So basically I'm just summing every product that was computed here, and I'm going to do the same for the cosine. And as you can see here, we knew that the frequency 4 was used to create this function, both with a sine and a cosine. And now we have 500 points, or the sum of the products were 500 for each one of them. That means that those 2 components are present in the signal. In this code here, I just use basically the same idea, but changing omega to 3. And then when we sum them, when we sum the function, now we have 0, something near 0. It's negative because it's probably a very low negative value, but it approaches 0 in this case. So this procedure allows us to understand that our function has 4 Hertz patterns, while the 3 Hertz is absent, so we could not find it. Let us plot this those 2 match products, but just for the sine, to see this effect. So when we plot the function against all the product between the function and a sine of 3 Hertz, what we have is this dotted or dashed line in red here. So some points of the function match with them, so we have a high value here, but some of them are completely different, so they have a negative value because they are on the in the opposite here, opposite sides regarding the zero value here. The negative values cancel out the positive ones, so that's why we have a very low number, in this case near zero, when we sum them all. Now when I plot the same function but with the sign of 4, we know that in this case we have 500, so it must be that many of those points are above the zero value. Now we can code a function in order to measure these ideas, but not for fixed frequencies, for a lot of frequencies or any range of frequencies that we want. So this I'm going to name it match freaks, and then for each frequency omega in a range of values between 0 and some maximum frequency, I'm going to compute the sum of f of the sines of omega times 2 pi t, and I'm going to do the same with the cosine. I'm going to print everything. So let's say that we have some frequency omega, and then I'm going to show the first is the sine, the sum of the sine, and then the sum of the cosines. So omega and that's it, that's the function. And then I can use this function here to evaluate, for instance, my function using t as a parameter, and then for 22 up to the frequency 22 hertz. And this is the output. As we can see here, it was able to detect that at 1 hertz we have the sine, at 4 hertz we have both sine and cosine, and at 18 hertz we have just the cosine as a component of the function. This means that if we stored just the values that are not zero here, we are going to be able to reconstruct the function, the same function, but just by using those coefficients. And this is the power of the frequency analysis. Let us see how we can do that, but by using images. In images, we don't have this type of like fixed or well-behaved functions that as we did here. So this is just like a function that we created artificially by using sines and cosines. But we have instead values that can vary or can have real values. What we are going to look for is that frequencies related to low values of frequencies are going to be related to smooth transitions, while higher frequencies are going to be related to abrupt changes along x or along x and y. So I can understand or I can study a type of something like this by interpreting it as, if I have lots of frequencies in the low part or very low values of frequencies, that means that that image has a more smooth characteristic. While if the image has higher frequencies, this means that the image has abrupt changes on the intensities. That means, for instance, a texture or a noise. I'm going to show a few of those, a few images and a few examples of those. So we have, for example, those three images here. So the first one is a ramp of intensity. So it starts with 255 and it ends on the other end here at 0. And then I added noise. So it's basically a ramp with noise. The second one has lots of patterns. Some of them are flat, so I don't have any intensity change. For example, here in this region, in this gray region here. And the third one have a smooth transition between intensity values. So it starts at 0 here, and then it goes up to 255 and then goes down again to 0. If we plot the image values, for example, for the first image, this is this one, and we just plot a section of it or a sub-image, we can see that it has the property that I just described. So in this corner here, I have a higher value, closer to a brighter pixel, and in this corner here, a lower value related to a darker pixel. And then it behaves like a ramp, but it has variations because of the noise that is present in the image. Let us do the same with the other images. So the second one here, so I just taken a part of it, and it has a similar behavior in terms of the ramp here, but a lower. Oh no, I just showed you the wrong one. Yeah. So in this case, I show you a part of the image that is constant. So probably it's something like here. So in this corner here. So it's just 1, 2, 7 along all this rectangle. So this means the image has no, locally in this region here, it has no variations at all. And finally, for the third image, so we see here is also a kind of there's a change in the intensity values, but this change is much more well behaved. It has no noise, so it goes from 8 to 4 and to 3 and 7, and then goes up 11, 15, 19, and so on and so forth. So how can we use frequency analysis to understand this type of images? Let us, instead of using directly the images, take a vector containing a few examples of it. So I'm just fixing the coordinate 100 here. So x is 100. So x equals to 100. And then y varies between 64 and 19.1. And then because this point here is not included in the interval. So I'm showing you the first examples here. So I'm printing the first examples, and it behaves as we noted in the image. And then when I plot this value, we can see that when I fix one line here, and I observe the variation along this axis y, I can see that it starts to decrease, goes down to 0, and then increases up to 100 and something, and then it starts to decrease again. So by inspecting this plot here, this type of image, what can we infer about the transitions of the intensity? Is it an abrupt transition, a fast transition, or a slow transition, or a smooth transition? So that's something that we are interested in finding when we do a frequency analysis. Let us do the same but for the other images. So this one here is for the second image. So it's in the middle of the image, so there is a ramp here also, but it's much there is a few a few pixels probably are noisier here, so it's not a perfect ramp. We could change to another region of the image. Would be this the same region that we defined here, so a constant value, and see that in this case the 1D function has no change at all. And finally, for the first image that is noisy, we can see that the intensity values change very abruptly. So the idea behind this, or the idea behind these examples, are to show you that in fact images can be seen as having patterns of repetitions and oscillations along its axis. So in the first case we have a smooth transition between intensities. In the second one we don't have any transition. And in the third one we have a very abrupt transition in between pixels locally. So by analyzing how the pixels change along coordinates, we can describe the image using frequencies. This allows us to a new representation, so to see a new representation of the image, but also it is a tool for image processing, as we are going to see in the next video.